A very good evening to all the participants in today's webinar on cell modeling using electrochemical impedance spectroscopy. So, this webinar will be a brief overview on how much more advanced topic, more advanced method of analysis can be used to determine uh, the prognosis and basically the deterioration or degradation of a lithium ion cell. So till now, till today, in many of our past webinars from Decibels, we have focused a lot on DC methods, that is direct current methods, where we have talked about DCIR or HPPC, that is pulse power characterization, and cell testing and characterization using DC equipments. But this webinar is a little bit different. We will not be focusing on the mainstream characterization, that is to say, the standard way of characterization. This method or this principle, this type of uh, testing and characterization is slightly special because it uses a slightly different method. Um, so we will in this webinar we will be exploring some basics of why impedance spectroscopy is important in diagnosing the cell's condition, like how fresh it is or how old it is, how much it has degraded, the lifespan of the cell, and how we can create cell models using the electrochemical impedance spectroscopy data. So in today's content, we'll be starting with like understanding some very brief basics on how ACIR and EIS can be used, like comparison of the two, just a brief introduction. Because when we come to impedance spectroscopy, there are two types. One is ACIR and one is EIS, and each one is created for a very specific reason or for a very specific purpose. They both are not the same. So what is the difference between these two and where they are used? We will be exploring this. And then what is the significance of using EIS or basically just impedance spectroscopy in lithium ion cells analysis? So why do we use EIS? Then we come to EIS testing. So basically there are two types of tests, or you can say two approaches to conduct EIS test. Basically it is dependent on the control mode. So either it is voltage control or current control, and accordingly we are classifying them as potentiostatic or galvanostatic. Then we are coming to the core part of the webinar, that is understanding how the Nyquist plot is going to be observed, because that is the output of the EIS test. If you conduct an EIS test, the expected outcome is basically an impedance graph, and that impedance graph is known as a Nyquist plot. They have certain regions, frequency regions, you can say, and we will be observing those with respect to a graph. So once we're done with that, we'll have an overview on the RC model, the equivalent circuit model, in which we will be having like two types. So RC model, very basic first order RC model, and then also an overview on how the Randles model look like. So also some conclusions, how and why we can how and why we can use them for further SOH estimation and things like that. So that is a brief description of today's webinar content. Okay, so beginning with the ACIR versus EIS. So as briefly introduced before, there are two methods of performing an impedance spectroscopy. So one is using a method called as ACIR, or also abbreviated as alternating current internal resistance, and EIS, which we know it stands for electrochemical impedance spectroscopy. So each one has been developed for a specific purpose, and each one like has its own like features and limitations and ranges. So to begin with ACIR, it's very simple. So ACIR basically it's a type of test which just produces a current frequency or a voltage frequency at 1 kilohertz. It's an AC signal that is produced by an oscilloscope, and basically that with the help of two terminal wires or with the help of two probes, we are able to put the probes on the terminals of the battery, and we are able to measure the impedance. So what type of impedance? We're measuring the AC impedance. So both methods, whether it is ACIR or EIS, will result in impedance of the device that we're testing. So mainly, this is conducted at a fixed frequency and at a fixed magnitude that is fixed at 1 kilohertz frequency. So this particular one is this method ACIR. It is used for a battery level, not for an individual cell level. Usually it is used for a battery level, for like basically you can say during the end of line testing when the battery packs are being assembled and sorted out. So like we go for grading, so capacity grading and internal resistance grading. So when we go for grading, the internal resistance is always measured using this method, ACIR. So the set frequency at 1 kilohertz, the probes are put at the terminals of the battery, and in less than 1 second, we get the impedance value of the battery pack. And not just for the pack, even for every series connection or parallel connection, whatever is there, we are able to obtain the AC impedance at 1 kilohertz. Okay. So this is a very fast method of testing the impedance for large number of batteries. So instead of like using DC method, which usually takes hours, sometimes it takes days also. So there is a very quick and fast method that is using ACIR. We're able to immediately get the impedance of the battery using ACIR, and that way we're able to instantly sort out all the cells, all the batteries at the end of the line. So before it goes into assembly. That is a bit about ACIR. But if we are talking about research and development, or if you're talking about development of algorithms, estimating the age of the cell, or diagnosis or prognosis of the cell's degradation, then we cannot use ACIR as it is. We have to focus on EIS. So electrochemical impedance spectroscopy, where you can see that your input is not fixed at 1 kilohertz. Rather, it changes from like a very small frequency, like in from millihertz to it changes to kilohertz. So sometimes you can say the equipment is rated even up to like 10 megahertz or 20 megahertz. So from very small frequency values to very high frequency values. So later on in this in this like as we progress in the content today, we will see why that's the case. So each point, each frequency has its purpose, or rather, there's a frequency range, and each of this range actually has a purpose. So the input in this case again can either be an AC current input or a AC voltage input, and the output depending upon the input. If it's AC current, output will be AC voltage. Accordingly, from there we can measure the impedance Z. Right. So this is usually like more focused towards the cell level, or you can even say electrode level for dual electrode systems or for single electrode systems, usually where more in-depth analysis will be done. Specifically, like you can say, where we have to measure the change in structure of the cell, or change in the impedance, change in the electrochemical behavior of the cell, the ionic interactions, how the ions are behaving inside. This kind of approach is used. So it's much more time consuming. It's very tedious actually, because we see here that the frequency is very low. Sometimes it can be lesser than this as well. It can go up to 1 millihertz also. If you have to run an entire batch of EIS test, say from start to finish, then it will take like maybe more than a day and a half to run the complete test, right? So this is where it is like you can say that it is most suitable for R&D work. So most suitable for development of, you can say, algorithms or estimation and prediction of health of the cell, like predicting the end of the life, useful runtime, things like that. Okay. So how exactly this is going to be used for cell health analysis, we will see in the later part of the session, where we are going to like bring in the concept of cell model as well, and also analyze some technical part of the nyquist plots, which is the output of EIS. Okay, so we conduct EIS for the purpose of research and development, and to see how the cell's health goes on degrading over time. Right. So like coming to the question, why use EIS? Why exactly is this method preferred? Like I had talked that initially, I will like in many of our past webinars, we had focused on the DC method of implementing like the cell characterization to determine the cell behavior, to see how the state of health can be estimated using the DC methods. But sometimes DC method is not reliable. It's not exactly that accurate sometimes. So that's where the EIS method is like much more advantageous. Like we can see a comparison of some of the methods of analyzing a lithium ion cell. So there are two types, mainly a destructive analysis and a non-destructive analysis. The destructive analysis, basically it's the name is self-explanatory. It means that you have to take the cell and you have to cut it open, and then which part you cut open, whether it's the anode or it's the cathode, it's the jelly electrolyte, or if it's the separator, or if it's the current collector. Each one has its own property, its own material, with its own behavior, with its own uh, uh, material science and the way it behaves. And accordingly, there are some techniques as well: X-ray diffraction, Raman spectroscopy, X-ray spectroscopy, scanning electron microscope, which is like a very detailed and expensive, time-consuming method of analyzing the cell. And also, it is not a practical way of say that like to analyze a cell's condition. You can do it only on a test bench. You cannot do this. Let's say if you want to develop a vehicle and you want to analyze the health of the cell or the condition of the cell, destructive analysis is not a method that is usually preferred, right? So this is okay if we are going for uh, like test bench, and there is no restriction of time, there is no restriction in terms of like the investments as well. Then definitely destructive analysis can be used. But of course, the priority is towards practical applications, real-time applications. So we have to go for non-destructive methods. And in that, of course, we have seen there is a DC way, that is direct current method, where we analyze the change in voltage over time, and from there we can estimate the resistance and things like that. Then we can go for electrochemical impedance spectroscopy, where we apply AC voltage signals, and from there we get the impedance. Then we have DCIR or HPPC, which is a testing method, the cell testing method. So these are the non-destructive ways, and usually electrochemical impedance spectroscopy almost always results in very accurate estimation of the cell's state of health, because at this point it is giving more information than DC methods. The DC method actually like it gives very like some very brief overview of what is the situation inside the cell, but it doesn't give the complete information. Electrochemical impedance spectroscopy gives the complete information of the cell, what all is happening inside the cell. But we will find that out as we go on to the next slides. So, yeah, that is why electrochemical impedance spectroscopy is used. It is it is a very sophisticated method which doesn't need you to break open the cell or cut open the cell or perform any destructive analysis. It just you need to have an oscilloscope that provides you an AC signal and then returns the impedance. So further elaborating into EIS testing, if you go into EIS types of testing, you can say, and then there are two types. One is a potentiostatic method, and the other one is a galvanostatic method. It depends upon like what kind of control methodology you want to use, and also it depends upon the what type of system we're analyzing. So it depends. Like for example, if the application is um, say having a higher impedance, which is like not exactly something related to lithium ion cells, then in that case, potentiostatic method is useful, where your input will be an AC voltage signal, your output will be an AC current signal, and yeah, from this you can derive the impedance. And usually this will be of higher order impedance, like usually will be 10 ohms or maybe something like 50 ohms, something that is on the much higher range. Maybe it could be higher than that also. Then we have the galvanostatic method, which is the other way around. We use an input of AC current and get an output of AC voltage signal, and yeah, from there the impedance can be estimated. And this is useful for systems which are having by design a much lower impedance. Say for example, a lithium ion cell, they come under the category of low impedance because they are usually in milliohms. They are almost always in milliohms. So if you take a battery pack, or if you take an individual cell, you will see that their resistance is in milliohms. So for that purpose, the galvanostatic method is most suitable. Okay. So as to why it is most suitable, there is like um, uh, there is like a lot of mathematical reasoning where we have to derive like transfer functions and see input to output relationships and things like that. It is not within the scope of this webinar as of now. So, but galvanostatic method is a much more stable and much more suitable method for lithium ion cells since they're having low impedance. Okay. On the left hand side, you can see there are some equipment. These are the equipments that are able to create the AC signals. These are oscilloscopes basically. Uh, they're able to provide the AC signals using these probes. You can see that there are two probes, like a positive and a negative probe, and in between you can place the lithium ion cell, and from here it will basically provide you the AC signal. Right. So from here you get the impedance uh, as a return. It calculates the impedance utilizing like some Fourier transform and things like that. So again, it is not something that will be discussed within this webinar. So when we conduct an EIS test, an electrochemical impedance spectroscopy, uh, so like we get the output as a Nyquist plot. Okay, so Nyquist plot is, we will see further on what exactly a Nyquist plot means, and what is the inference from Nyquist plot. So basically, we conduct a EIS test such that we provide excitation current. We can also call it as a perturbation signal to a lithium-ion battery. Then we get a voltage response. We utilize the equation Z is equal to V by I, or you can say V is equal to I into Z. So from there, we perform a Fourier transform or fast Fourier transform, FFT, you can say, converting that from time domain to frequency domain data. And once that is done, we are able to obtain the Z, that is the impedance Z, uh, as something called as an impedance spectrum. Okay. So like it is called as an impedance spectrum because it is able to, we are able to get the impedance as uh, a- as a as a set of series, or you can say within a specific range. So you can see here it's not just one value of impedance, it is a set of values of impedance that we are obtaining from this test, and therefore it is called as a spectrum because it is conducted at different frequencies. So yeah, this is the inference from the EIS test. The output that we get is a Nyquist plot. And you don't just get Nyquist plots, we get Bode plots also, which is magnitude versus frequency. And that will help us determine like different components within the cell, like how they are and what are the different contributing factors to the impedance in the cell. Okay. So as a brief overview of what exactly is EIS and what is the output from EIS, till here we are able to visualize this. So Nyquist plot, to further elaborate on this. So Nyquist plot is basically a plot that shows the total impedance of the cell, which is usually a combination of a real versus a real and imaginary impedance. The reason being is that it doesn't just return a singular value. It's not just one single value, unlike in DC values where you get like a single value. And in this case, it gives you multiple values. That's why it is called as a spectrum. And that usually is a combination of imaginary and real impedance. The reason is because each component has its own response to the AC input, that is the AC signal input. And many times you will notice that the response is not in phase. So like we know that like we have AC signals that are used as an input, and correspondingly the output will be either in phase or out of phase. So if you're having in phase, out of phase, and if you're having like each component that has its own behavior, then it is contributed in two parts. One is on the imaginary part and one is on the real part. Okay, that is basically what you can see here on the left hand side. The graph actually represents uh, the Nyquist plot, and you can see that the frequencies that was talked about earlier, the low frequency and the high frequency and different types of frequency, each frequency reveals a particular phenomena which is observed within the cell and what kind of impedance it contributes. Basically, you're able to observe that. Okay. So here on the diagram, you're able to observe that at low frequencies, which is marked here in the black region, this is the low frequency and it's basically a straight 45-degree line. It's a 45-degree line that you're observing here. So this particular portion represents the impedance contributed by diffusion. Okay, so you can see over here, it is marked as ionic diffusion. Okay, and usually this is measured like at very low frequency regions, but like 0.01 hertz, to around 1 hertz to maybe 2 hertz. It's very low frequency, and this particular frequency is sometimes very challenging to perform. It requires a very competent device, a very capable of device of of a very powerful device in order to do this kind of test at very low frequencies. Then we have the mid region, which is from 1 hertz onwards to about 600 hertz. So it's a much larger frequency range, and that you can notice in the center, which is represented by a semicircle. It's not exactly a semicircle, it is an approximate semicircle, and that represents a set of chemical reactions that happen inside, which are known as charge transfer reactions, and also a combination of the solid electrolyte interface. So this will be further elaborated in the next slide. So we'll be talking a little bit more about the reactions and what exactly is the reaction have to do with the impedance and things like that. Then at high frequency, so that is above 600 hertz, nearing to the value of 1 kilohertz, we get to the point where the electrolyte starts to provide impedance, and that is observed at this point. So the point where the impedance graph that you're seeing here, the semicircle, it basically intersects with the zero line. So if you observe the zero line, this is the zero line, and where the zero line and the Nyquist plot intersect, that point is known as the electrolyte impedance. Or rather, you can say the distance between this point and this point is known as the electrolyte impedance. That is the impedance provided by the electrolyte within the cell. Okay. And then when we even increase the frequency even further, so beyond 1 kilohertz to about 5 kilohertz or 10 kilohertz, we then come across the inductance. So basically, this is due to the metals present within the cell. Okay. So this is the different regions within different regions of the Nyquist plot. And this is why, like Nyquist plots, I mean, this is why the EIS test is so much more detailed and so much more useful compared to the DC methods. The DC methods do not reveal any of this. They just reveal an approximate voltage drop due to a current signal, a DC current signal, and that returns the resistance. But each one of these parts, each one of these frequency parts that we see, low, mid, and high and ultra high, they return a certain impedance corresponding to each and every component of the cell. Okay, which is why EIS is so much more useful in terms of like analyzing a cell. Okay. So if we go and dive a little bit more deeper into the contribution of each impedance, we observe here ionic diffusion is basically the process in which the ions enter the anode or cathode. Basically, they enter the electrode, and when they settle into the active material, there is a certain resistance, or you can say impedance, faced during diffusion due to the structure of the material, and that leads to what is called as a diffusion impedance. And in technical terms, this is called as Warburg diffusion. Okay. So this element, or rather you can say this type of impedance actually has one of the highest magnitudes in terms of the impedance contribution. Later on, like we will see like how that's the case. As I will explore the MATLAB code, we will be able to see there how exactly that's the case. Then once the ionic diffusion part has been established, like then we go to the charge transfer impedance. Okay. So charge transfer has to deal with the reaction. It's basically a chemical reaction that takes place within the cell. So a little bit about this, we talk about redox reactions. So in terms of redox reactions, either you gain electrons or you lose electrons, depending upon which type of reaction it is, whether it's reduction or oxidation. If it is oxidation, it is a loss of electrons. If it is reduction, it is the gain of electrons. So during the gain of electrons, or during the process in which electrons are absorbed, the ion is converted into an atom, into a complete atom within the structure. So you can see within the structure, you have all these blue color dots, and they're all your atoms. They're all basically ions, and they're going to be converted into atoms when they absorb an electron. Okay. So this part is known as charge transfer, and during this phenomenon, some impedance is faced by the ions when they are going to absorb an electron, and therefore that is known as charge transfer impedance. Okay, so that is one part, and the second part is kind of coupled to this. It is called as solid electrolyte interface impedance. So that is mostly almost always experienced at the anode surface. So you can see the left hand side that is marked as anode. So there is a green color plate or a green color surface that has been put there that signifies what is called as SEI, solid electrolyte interface. It is a layer that develops because of the deterioration of electrolyte. So when the electrolyte decomposes slowly, or when the electrolyte undergoes aging, or you can say it undergoes decomposition, it starts to deposit some compounds or some sort of layer onto the anode surface. And this can also act as a hindrance. It can also act as some sort of an impedance. So once again, your Nyquist plot is able to reveal this. Okay. So together, charge transfer and solid electrolyte interface is revealed in the semicircle that was introduced earlier. So we had talked about a semicircle. So usually for fresh cells or for brand new batteries and brand new cells, these two together they form one single semicircle. And as and when the cell goes on aging, as and when the cell goes on degrading, undergoes cyclic aging or storage aging, anything, the ACI layer starts to form and it starts to become more and more thick. So that is once again revealed by the Nyquist plot. Okay, so then as we move again towards higher frequencies, we had mentioned electrolyte impedance. We had seen that this is one of the contributing factors. So basically, this is the segment where the spectrum will reveal the contribution of electrolyte impedance. So that is you can see the bluish medium within the cell over here. So basically, this is the medium through which the charge or basically the ions are transferred between the anode and cathode or back from cathode to anode. And this portion also has an impedance which is revealed at high frequencies. Then at much higher frequencies, we go to the much more atomic or subatomic components that are basically metallic, and current collectors, additives, then metals within the anode and cathode itself will provide what is called as inductive impedance. Okay, and usually this inductive impedance is low. It's not a major contributor, but it is observed at high frequencies. Okay. So this is the complete information on what a Nyquist plot will reveal. So as to why we are validating EIS as a very detailed and a much more preferable method. So this is why it's able to give the condition of all these um, different components: the cathode, the anode, the electrolyte, the solid electrolyte interface, the inductive components, the condition of the electrodes and the electrolyte. So this is what this EIS testing is able to reveal. Okay. So, how do we then relate the Nyquist plot to an equivalent circuit model? So, how we are able to represent all these processes as something that is more visualizable, something much more easier to understand. Basically, mm, you can represent each of these components as a series of resistors and capacitors, resistors, inductors, and capacitors, depending upon how you want to represent them. So, if you want to go for, let's say, a very simple and a very, like you can say, a zeroth order or a simple first order model, then you can use what is called as a simplified RC model. Okay, so simplified RC model is just exactly like how you create an RC model for DC circuits. You're representing R naught as a ohmic resistance and an RC pair that represents the semicircle over here. Okay, so you can see that is marked with the numbers region 1 and region 3. So region 1 talks about your electrolyte impedance, and that is represented by R naught over here. And here you can see region 3, which is simplified as a pair of R and C elements, a resistor and capacitor elements. Okay, so it's a very simple way of doing it. You're kind of approximating all these impedance values as a series of resistors and capacitors. But this model doesn't exactly do justice to the the complexity that is being represented here by the Nyquist plot. So therefore, we use another approach which is called as Randall's first order model. So Randall's first order model is basically a much more elaborate model. It even introduces the concept of inductance, okay, which is represented by this region number 2. Okay, and then you can see that there is a change here in region 3. So in the previous model, that is a simplified RC model, we had just talked about resistor and capacitor. But in case of the Randall's model, we do not use capacitor as such. We use a much more advanced element, a sort of a non-standard element. It's not exactly an electrical element. This is called as a constant phase element, which is abbreviated as CPE. So constant phase element is an element that represents a non-ideal capacitor. Okay. The scope of understanding capacitors and non-ideal capacitors within electrochemical devices is not in this webinar as of now. Um, but just to clarify the difference between Randall's model and a simple RC model, instead of using a capacitor, we instead use what is called as a constant phase element, and that is slightly different from that of a ideal capacitor. This is what is known as a non-ideal capacitor. Okay, so then we come to the diffusion part, which is represented in region 4. Okay, so as explained earlier, this was called as diffusion impedance, and the particular term for this is called as Warburg diffusion or Warburg impedance, and that is represented by the element W. Okay. So again, this is a non-standard electrical reference. It is not exactly something that is representable directly. We cannot use any element that directly represents Warburg. So sometimes what happens is that this Warburg is then represented as a series of RNC pairs as well. So you can have like 3 RC or 4 RC pairs that are substituted in the case of like the Warburg element, and you have what is called as a Randall's first order model in this case. Okay, so this is how we represent the uh, equivalent circuit model uh, in electrically in terms of the electrochemical processes. Okay, so this is how we simplify all of them, and this is how we are able to represent every single process or every single component within the Nyquist plot as electrical elements. Okay, so again, to further talk about the diffusion processes itself, it depends upon what kind of diffusion happens. Whether you're talking about uh, idealistic diffusion or non-ideal diffusion, it depends. So there are classification of diffusion itself. Maybe you are seeing like something that is marked here as semi-infinite. So semi-infinite diffusion is basically, it talks about the distance of diffusion, basically the thickness of the electrodes, either the anode or the cathode, within which the ion is undergoing diffusion, and whether it is an infinite diffusion or infinite thickness or semi-infinite thickness or limited thickness. Based on that category, we can categorize the Warburg element here. Okay, so once again, uh, uh, we will not be going too much detail into the types of diffusions and all. It is not exactly within the scope. The idea is not to go too much in depth. Rather, it is to understand how we can relate impedance diagrams to electrical elements that we can create a electrical circuit from. Okay, so this is how we represent all of the electrochemical processes as electrical elements. So yeah, now we can have a quick overview of the MATLAB script that has been developed in order to analyze this Nyquist plot. So this has been done in order to post-process the data. So once the EIS testing has been done and the Nyquist plot has been obtained from the device, further onwards, like other information has been derived from here. Say, for example, the constant phase elements, the circular frequency values, the Warburg diffusion, and all these things. So just to show you the like graphical outputs, how exactly they look like, we can have an overview here. Yeah, so if you observe here, this is the first output. Basically, this is the like set of Nyquist plots that you get based on the SOC. So you can see how much difference there is every time the SOC changes. So like at step intervals of 5% SOC, we are conducting an electrochemical impedance spectroscopy. And here is how we are obtaining the Nyquist plot. And then you can see every time the SOC changes, there is a very big influence on the charge transfer and the capacitance, the charge transfer resistance. You can see the diameter of the circle goes on increasing. Okay. So the next plots that we have here, this is how the ohmic resistance, that is the electrolyte resistance, and the charge transfer resistance, that is R1, change with respect to SOC. Okay, so once again, you're able to observe this sort of polynomially increasing trend line. So this can be like further on represented using some like curve fitting analysis and all these things. Okay. So this is how the two major elements that we usually use for cell state of health analysis can be represented, because it is actually these two elements that are like more in focus during the testing part and during the algorithm development part, that is usually utilized for SOH analysis. So then we have some constants here. So basically, just to give a quick overview, these are constants that have to do with basically the time constant and things like that. So time constant is basically related to the diffusion process and all those. So that is represented by TCP and PCP, and this has to do with again estimating the constant phase elements CPE. Okay, so then we come to estimating the constant phase element impedance. So that is represented over here. Okay, so how again this fluctuates with respect to SOC. So eventually this is the semicircle region. So this is how the impedance will look like if you analyze the semicircle region at different SOC values. Okay, so this is for your constant phase element impedance values. And then we have the Warburg diffusion, ZW. Okay, so as described earlier, like you can see actually that Warburg diffusion is the one that contributes to, you can say, the maximum amount of impedance, the maximum contribution of the total cell impedance. So this is how the impedance characteristic looks like once you perform the Warburg diffusion analysis at each SOC value. Okay, so this is how the characterization can be done in order to categorize each and every element, each and every impedance contributed by each and every element. So this way, like you can actually feed all of these values as a lookup table. So which you can see on the right hand side. You can see these are the values actually, and you can see these are in the complex format. So these are not real values. These are real and imaginary put together. So they're in the complex. They're in the imaginary and real, so complex domain basically. Okay, so only R0 and R1 you are able to observe that they're in real domain, but rest of them, that is ZW and ZCP and even L, they're all in the complex domain. Okay, so you can see this. So ZW is here, ZCP is also going to be in the complex domain. So, but for the time being, it has been taken as real values. Okay, it has been converted back into real. Then you can see here the impedance values as well. Okay, so once again, this has been converted into real values. So you can choose which part of the impedance spectrum you want to use as to terms of modeling, whether you want to choose the impedance only related to real part, or whether you want to choose it only with respect to complex part, or whether you want to represent both. You have that choice. Okay. So once we have the lookup values all over here, all the imaginary and real impedance values, you can then feed it into the equivalent circuit model that we develop. Either you can develop that in Simulink, or you can develop that in any simulation platform. And then you can feed them into these individual elements you can see here. So R0, inductance, RCP, and Warburg. Okay. So this is how we were able to utilize MATLAB as an efficient tool to analyze how to derive the RC and L values and even the Warburg impedance values and feed them into the equivalent circuit model. Okay, so then the question now comes, like, how exactly is Nyquist plot helpful in analyzing the condition of the cell? So as the cell goes on aging, like you can see here on the left side, there's a diagram that represents the aging of the cell. And over the cycle number, you can see that the charge transfer, that is the semicircle representing the charge transfer resistance, the charge transfer impedance, the diameter of that part goes on increasing. So you can see initially it is just this much. But in terms of like age cell, you can notice it is here. So that is one of the most prominent outcomes. Once you conduct an EIS at regular intervals, you're able to observe the continuous change in the charge transfer resistance along with the ACI layer as well. So slowly, you can even observe that there is a second semicircle that will eventually develop along with this major one. And that represents what is called as ACI layer or solid electrolyte interface. Okay. So by observing the change in these following parameters, that is ohmic resistance or charge transfer resistance or ACI layer or even Warburg impedance, you're able to analyze the condition of the cell and then you're able to relate it to the SOH. So that is given by this. Okay. So here you can have an overview of how the graph is characterized uh, over over the cycle numbers, over the SOC, and over temperature. So all of this has been experimentally determined and over like continuous cycling and at different SOC values and at different temperature values. The values of the charge transfer resistance, as an example, has been plotted here. And there are some interpolating functions or some polynomial functions that can be derived by performing curve fitting. And then from there onwards, you are able to derive RCT as a function of SOC, temperature, and cycle number. And from there onwards, you're able to create a model that gives you an SOH estimate. Okay. So this is how you are able to effectively utilize Nyquist plots to analyze the contribution of each process, electrochemical process within the cell, and then derive each of the components, RC components, and focus on any one component, for example, say charge transfer, and derive its variation with respect to cycle count, temperature, and SOC, as you can see on the left hand side, and then feed that into an SOH estimation model. Okay, so which the equivalent circuit model will actually do. So SOH estimation can be represented utilizing this equation. Okay, so the RCT, which is observed at the very end of its life, at usually at 80% capacity, what is the charge transfer measured at that point, minus the present value, which has been estimated from this function, divided by the difference between end value and fresh value. Okay, so this is how actually we are able to go for like implementation of EIS data in an equivalent circuit model to estimate the state of health. Okay, so this is how we are able to effectively conduct EIS tests. So basically, they are able to reveal a very good amount of information and how the cell components go on degrading over time, and then we are able to more accurately visualize how RCT or any other component for that fact changes with respect to all these values, right? So number of cycles or temperature or SOC, and then utilize it in an SOH estimation model. Okay. So like one of the other fitting methods that you can use, you don't have to necessarily use MATLAB. You can even use ZView as well, which will return the values of the RC values, basically the inductance values, the resistive values, capacitive values, the Warburg values. And from there also you can implement that in an SOH estimation model and obtain the SOH of the cell. Okay. So there are many software platforms that are able to derive the RC values by performing curve fitting and give the RC values as results. Okay. So just an example is ZView. There are some other ones as well, like Metrome or Biologic, which are able to do it. Yeah. So this is actually is a very brief overview of how we can utilize EIS for cell modeling, electrochemical impedance for cell modeling and cell state of health estimation.